Hello everyone, welcome to the ECE5973 class, and the whole class is about printed circuit board design principles and practices. Starting with short biography about the lecturer. My name is Walid. Um, I hold a Bachelor and Master of Science degrees in Electronics Engineering, and I hold a PhD degree in Electrical and Computer Engineering from University of Oklahoma. I started my full-time career job in 2005 as a hardware design engineer and also a circuit design engineer. I have long-term teaching and training experience. I taught university classes in embedded system development, PCB design, computer-aided design, and control system, and several other classes for EE students. I have over 14 years accumulated experience in hardware design and embedded systems development. Currently, I work as a senior principal research engineer at Panduit Corporate Research Center or Innovation Center in Tinley Park, Illinois, United States. Now, what is the course about? So, the objective of this course is to bridge the gap between industry and academy. We see in industry a lot of fresh graduate engineer that lack of experience, and we had we have to put those engineers into training for several months before they are able to contribute to a real project. So if we can transfer part of this experience to academy, that would be great to bridge this gap. And in this case, we can help our future engineer to build the right skills for their future engineering career as PCB designer or hardware design engineer or circuit design engineer or whatever the title of that job. So also we will provide a variety of essential and in-depth topics during this class to advance the students' knowledge of designing a printed circuit board using one of the most uh, magnificent PCB design tools, which is Altium Designer. Of course, we will dive into more challenging topics, including mixed signal design, printed circuit board design considerations, um, and another technical topics like signal integrity, including differential pairs, links matching, crosstalk, etc. Also, we'll cover all the essential topics needed to build a highly reliable printed circuit board that can work from the first time, and we will use, of course, Altium Designer. So the question would rise at this point: what is the future of a PCB design engineer or hardware design engineer? Now, if you look at the era of Internet of Things or IoT as it's called, so the need to design current and evolving a product or PCB technology is growing. It's growing, actually rapidly growing. With more and more electronics such as Internet of Things, cell phones, etc., that become every day of our lives, the future of electronic design is very, very bright. Now, the industry needs more PCB designer, and those are currently involved are reporting that their compensation and job satisfaction are on the rise. If you look at this survey in here, you will be amazed by the salary offered for PCB or hardware design engineer. So, do you have a passion to create things and making them work? If so, then designing a printed circuit board may be what you are looking for. You will have much better success as a PCB designer if you have a degree that include courses in computer-aided design or printed circuit board design in your transcript. And this is what this course is all about. So the question is, what are the course topics? So the course topics might include and not limited to the following topics. And these are range between basic topics into very advanced topics. We will try during this course to simplify all these concepts and provide hands-on experience about their application using Altium Designer. And of course, we will start with introduction to the PCB design. What is the definition of PCB? What is the PCB anatomy? We'll go into details to understand the PCB in depth. And also, when we discuss a PCB design, we will discuss it not only from academic or theoretical perspective. We will learn PCB design by the same processes used in industry when we design products. So we'll talk about the processes as well, how we start from an idea and all the way to realization of a real product. So what are these processes? We will discuss these processes and we will try to implement them during our learning in here. Also, it's good for all of us to have a review about electronic components. What are the electronic components, various types of electronic components, how they are evolving over years, and what are the symbols and footprints for these components, because PCB design is all about symbols and footprints of electronic components to put together. Also, we'll learn how we can create component libraries to use them in PCB design. Then we will go over schematic and layout, design rule check, electrical rule check, and then we will start diving into more advanced topics that has to do with signal integrity, design practices, and other things like design for manufacturing, electromagnetic interference, electromagnetic compliance, and so on. So for session one today, the outline for this session is we will start with an introduction to PCB design. Then we will go over the PCB anatomy and all various components of the PCB or elements of the PCB. Then we will talk about how PCBs are being manufactured and assembled. We have a demo for that. Then we will go about over the processes we talked about, which is electronic design, manufacturing processes, how we design a real product. Then we'll end up with why we need to use Altium Designer. In industry, when you make a decision about using specific tools, there are a lot of elements that judgment your decision. So it's not like a random decision, you pick up a tools and move forward with that tools. No, there are a lot of factors you need to consider when select a tools, because the propagation of this decision will go over several years. So you need to be very careful about using the tool. So what are printed circuit boards? Basically, printed circuit board or PCBs are in every single piece of electronics in our daily life, starting from remote control, TVs, laptops, smart watches, fitness trackers, also Nest device, Alexa or Echo, the Amazon Echo, everywhere. It's in every single device, and that shows the importance of PCB design as a career job, because this career is evolving, will never expire. The complication is of these PCB is getting more and more complicated, and you need to keep evolving with the technology as well. So it's basically a structure, it's physical structure that hold electronic components and provide connectivity, electrical connectivity between various components on the board using something called conductive traces. Now these PCBs, usually you see them in green like this, and these are the electronic components. You see them for this Nest device. They can be either rigid or they can be flexible PCBs as well, like this one in fitness tracker. And they can be single-sided PCBs, and these single-sided PCBs were used in early 50s, 1950s, or double, meaning the traces will be on one side, and on the other side you will have the component soldered to the PCB. Now, double-sided PCB, you have traces or conductive traces on both sides, and the components can be also placed on both sides. More advanced PCBs in our today's technology, you will see multi-layer PCBs that have multiple layers encapsulated all into one rigid PCB, and you have traces on all layers. However, the components will be placed only on the top and bottom layer. And we will get into that more and more by moving into through this class. Now, basically, printed circuit board became popular in 1950s, and the need for PCB design engineers to create those circuits took off at that time. Originally, circuit boards were designed or laid out on the drafting board at 4 or even 10 times the actual size using tape, knives, stickers, and steady hands. That's it. And I used myself in around 1998 to do printed circuit board by my hand. So I need to draft that by my hand. And later I started using milling machine. Now, when completed after this drafting, the drawing will be recreated on a film using a reduction camera, and that film would be used to make the PCB tooling at the fabrication shop. Now today, rigid flex PCB layout is done on advanced computer-aided design systems such as Altium or Eagle CAD soft, and their output is used directly to create the PCB tooling. Basically, you draw your PCB design in Altium, generate manufacturing files, and then send these manufacturing files to the shop, and they will do the PCB for you. Now, as we can see here, some examples. On the right side, we can see Motorola Golden View, the most popular 7-inch television in late 1940. And it's also, you can see a PCB with 2 layers and electronic components on that PCB. This is one of the earliest applications of printed circuit board design. It can be traced back to 1948. Now here you can see how printed circuit board are designed in 1960 edition for an engineer drawing circuit board. As you can see, they used to do that drafting on a piece of paper, as I mentioned, and this piece of paper, after they finish drafting, they will do the films using the imaging cameras, and then they do the fabrication for that. And here also, late 1960, you can see one of the memory card for a calculator, the most famous calculator, which Wang model 362E. So you can see also the printed circuit board and the component distributed on that printed circuit board. Now, if you compare this printed circuit board to the today's printed circuit board, there is a huge differences. Now, what type of printed circuit board we expect to see? Now, starting from a rigid PCB, if you have motherboard on your computer, you will see a PCB that is really dense with electronic components, and this PCB might be composed of several layers and go up to 42 layers. Also inside the iPhone you can see, or your cell phone, you can see rigid PCB. The other type of PCB is called flexible PCB, as you can see in here, and we will talk about these, how we can design these boards in Altium Designer. It's very useful when you have like a fitness tracker where the PCB is surrounding your wrist. So it's good to have flex PCB because you will save space. The other type is called rigid flexible PCB, where you have 2 rigid PCBs and flex PCB in between, as you can see in this cube in here. So you have 1, 2, 3, 4, 5, 6, 7, 8 rigid PCBs, and all of them are connected together to form a cube by 1, 2, 3, 4, 5, 6, 7, also and 8 flex PCBs. So in this case, you don't need to have connectors, you don't need to have disconnectivity in your signals, and it's just one connection. So 7 flex PCB. The new type of PCB is called embedded PCB, where in addition to the component you have on the top and bottom layer, you have embedded components inside the PCB. Now, since the technology is evolving, the density and complexity of PCB is getting higher, they started putting components inside the PCB and embedding them inside the PCB to save some space, because the space on the top and bottom layer is limited. So instead of making the PCB layer, they started putting the component inside the PCB. Of course, this technology is very expensive till now. Now, how we can classify printed circuit board? They can be classified into three groups. The first group is based on the technology. As we mentioned earlier, they can be either single-sided PCB, where you have the conductive traces on one side of the PCB and the component are placed on the other side, and they will be soldered from the conductor side. The second technology is double-sided PCB, where you have traces on both sides, the top, bottom, and the top side and bottom side of the PCB, and the component can be on either side or on both sides as well. So multi-layer PCB, you have several layers that are all combined together to form the PCB, but the component will be only on the top and bottom side of the PCB. Embedded PCB, as mentioned earlier, we have, in addition to the component placed on the top and bottom side of the PCB, you have components that are embedded inside the PCB, such as memories, could be passive component or LCs, etc. Now, also we can categorize them based on the substrate. So the substrate, it can be rigid PCB, which is solid, hard PCB, or it can be flexible, or it can be a mix of rigid and flexible PCB. And the third category is based on the material used to construct the PCB itself. So it can be based on epoxy PCB. So the epoxy will be formed by glass fiber and resin, or it can be Teflon PCB, and these are expensive, but they are essential when it comes to high frequency design. If you have high frequency, like you have CPU that's running in 1 gigahertz, you have to go with this type of PCB, because epoxy PCB has a poor performance when it comes to high frequency. And also we have the other type of PCB, but the most famous types are the first two. Now, if we talk about the PCB anatomy, we start with substrate. So also it's called laminate. So basically, the cover that forms the traces on the PCB is held by a rigid board insulation material. This insulation material provides structural support to the circuit component and traces as well. So the thickness of this laminate material we see here, it's called FR4. It's high. Has a high dielectric constant, and it's also its isolation material or insulation material comes in different thicknesses. So the type is defined by specific thickness, and we will talk about that in the next slide. And the most commonly used laminate material is called FR4. When we go and try to order a PCB, as we will see later today, you need to select the substrate material, and FR4 is the least expensive and the most widely used material for laminate, and it comes by between 5 tau and 38 tau thick. Now, typically it consists of 2 sheets of cover, and also we have the laminate in between these two, or called glue. So this will hold the two cover cladding into this sheet in here. Now the thickness of the cover sheet also comes, we have 4 different options. The most widely available options are these. Either you have 1/4 ounce or half ounce or 1 ounce or 2 ounce. Now the most standard is 1 ounce. All the PCBs you see are using 1 ounce. Now high speed digital design required maybe half ounce for high speed signal layers, and power, when you have power layers that are responsible for distributing the board. They use 2 ounce, and we'll talk about that in place, not for now. But for now, you need to know that the common thickness of the cover is 1 ounce all the time. So basically, and it's 1 ounce of cover per square foot. That's why they call it 1 ounce. It's basically the thickness will come at 35 micrometer or 12 down. So basically, they put a layer of this cover or a sheet of this cover on the top and bottom of this laminate material and use a process, thermal process, to glue these two together and harden the epoxy material in between the two. As you can see here, and they call this as Prepreg. And after they put the cover on the top and bottom, they call it cover clad laminate, so which is composed of cover layers and is in addition to the resin glass fiber material in between the two. The prepreg is basically a kind of pre-impregnated bounding sheet, and this is goes through thermosettings resin plus fiberglass to create a sheet of insulation material, and they call it in industry B stage, which is semi-hardening state of resin. And it's a glue, basically it's glue, as we said earlier. It holds the two cores together, and it comes in different sizes based on the size of the mesh, as you can see in here, and the thickness as well. So the first type is called 1080, which has fine grit, and the class size of this is 50.8 micrometer. And the thickness after press, after they do the press and do the hardening stage, is between 60 to 70 micrometer. The second type is 2116, which has a little bit larger grid, and the size of it is double. As we can see, the size of the grid is double, and the thickness after press is almost double as well. The third type is 7628, and as we can see also, the glass size is 170, and the thickness after press between 180 and 190. So why we have different sizes? The reason for that is to control the thickness of the PCB and the spacing between the layer when you construct the PCB layers, as we will see later in something called stack up, PCB stack up. So the process for creating prepreg is, it's called, after all, you get the copper clad laminate, which is copper foil with prepreg and copper foil. So the copper foil on the top, copper foil on the bottom, and goes in through the thermosettings process, and it will harden, and now you get a PCB with 2 layers. Now if you need more layers, you need to have a core on the top or on the top and bottom, and have also another cover clad laminate, which create 2 layers. So always the PCBs comes in even number of layers: 2, 4, 6, 8, 10, 12, and so on. It cannot come in odd number of layers. It has to come in even number of layers. Always you have pre-break between 2 layers, and you have a core that separate 2 cover clad laminates. Now here are some examples for 4, 6, 8, and 10 layers. So as we can see, in 4 layers we have the cover clad laminate composed of 2 sheets of 1 ounce cover with 1 sheet of 2116 and 1 sheet 7628. If you add the thickness of this and this, which we talked about in here, so if you combine this and that, you will get the specific thickness for these. Now then you have also, these are the first layer, second layer, third layer, fourth layer. So this one is basically a copy of this, and now to combine this with that layer, you need to have a core material in between. So the core material is similar to this, but it's pre-hardened material. So the total thickness of this board will be around 1.6 millimeter, as we can see in here. Now, when it comes to 6 layers, the same case, you need always to have a core that separates the copper clad laminate. So we have 2 layers, we have a core, we have 2 laminates, we have a core, also we have 2 copper clad laminates, as we can see here. And the total thickness is the same, we have 1.6, but look here. Now, instead of using 2 layers of this laminate material, we are using only 1 layer because we have more layers now to combine together. Now, when it comes to 8 layers, we still have the same thickness. It's 93 tau. But now we have 8 layers and we have 3 cores to separate these layers, and the thickness of the core materials is like half now. Now when it comes 10 layers, also we have the same thickness, and we can see we still use 2116 laminate sheets, and we have now 4 cores to separate all these layers. Now if you go beyond 10 layers, the board thickness will become much higher. Or if you change the thickness of the cover from 1 ounce to 2 ounce, it will also become more thick. The board will become more thick. Now, when to use 2 ounce cover? I recommend that you take a look at this link. Here we can see a Giga board motherboard, and they are claiming 50 degrees C cooler than any other motherboard. And the reason for that, they use 2 ounce copper inner layer for power distribution on the motherboard. They have 2 ounce copper inner layer to distribute the power. They call this power ground layer, and they call this also ground layer. And this will reduce the power dissipation coming from the power distribution on the components and make the board even cooler, providing more current flow through these traces. The second element of the PCB is the traces, or are the traces that are used to electrically connect all the components on the board. And these traces are placed on the top and bottom and the inner layer of the PCB. And these are usually copper traces, and they can be created by one of the 3 different processes. The first one called photolithography, which required photomask, and we will see a video about the processes for making a PCB using this photolithography. The second one, they use laser if they need really fine traces. For high density printed circuit board, they started using laser to make these patterns on the photoresist. The third one is just for prototyping. It's called machine milling, using a milling machine, and we only use this for prototyping and nothing else. And the maximum you can create is 2 layers of PCB. Now, the traces widths and thicknesses are determined by 2 factors. The first factor, how much current this trace can hold, or the amp capacity. The second factor is the characteristic impedance of the trace, and we look into characteristic impedance when we talk RF, or high speed signals going through the traces, which is the second part of this class. We'll talk in details about signal integrity and impedance matching and so on. So there are also practical limitations, and it's very important part of the PCB design engineer responsibilities to find out what are the capabilities of the PCB manufacturing plan before starting PCB design. Because what is the minimum tray thickness? What is the minimum hole size? What is the minimal spacing between the traces? All these parameters has to be have to be determined before starting the PCB routing. Now, let's take a quick look here at an example if we have a circuit and we need to design traits that control, let's say, load, how much current we can put on that trace. We need to calculate for that. So for this, you can either look at the graphs that define the width versus the current, or you can use a calculator, which we are going to use during this class. And as you can see here, for specific thickness, which is 1 ounce cover here, if you have a trace, depends on the width. Let's say the width for this trace is 10 mil. The maximum current you can pass through this trace depends also on the temperature, change of temperature. At 10 degrees C change, you can pass up to. So it depends also how much you allow for the temperature to rise on the trace when the current pass through. So if you allow only 10 degrees C and you have, let's say, 10 mil trace, the maximum you can put through this trace is less than 1 amp. Now, if your trace is around, let's say, 10 mil as well, but you are allowing 70 degrees C increase in temperature on this trace due to the current, then you can put 2 amp in this case, but this is not recommended. So don't allow more than 10 degrees C to 15 degrees C increase in temperature due to the current flowing through the trace. So, and you need also to add 20% margin on the top of that. Don't design at the maximum boundaries or the absolute values all the time. This is bad design practices. So to calculate for that, we are not going to look into graphics or graphs. We are going to use one of the most famous PCB design toolkits or calculator to calculate the size of the vias, traces, spacing, etc. And I encourage you to download these tools from now because we are going to use it throughout the course. Now the third element of the PCB is the hole. The hole in general can be a via, can be a pad, can be mechanical holes, or sometimes they call them mounting holes, can be also cuts. And they can be either plated or non-plated. Plated meaning they have a cover all over. Non-plated, they are just mechanical holes. Here are all different types of the hole scenarios. So either we have with bad, meaning you have a bad on the top and bottom of the layer or the PCB where you can put solder into it, or without bads, as you can see here, it's just a cover plated inside the hole and nothing on the top and the bottom. Now, it also could be non-plated. You have a bad on the top, bad on the bottom, and there is no plating between the two, meaning there is no electrical connection between the top and bottom layer. And this condition could be seen in mechanical holes as well. This is not used for electrical component. And the third type is pure mechanical hole or cut out. It's non-plated hole. There is no cover on the top or inside this hole. If we go into more details about those holes, they are called as bad if they are not mechanical holes used for fixing the board. So the bads, basically they have an area, it's a cover on the top, or here we can see those SMT bads or surface mount bads or through hole bads to solder the component, or can be used for testing points. And they can have any shape. Usually they use shape coded holes or bads to define the positive and negative or the first pin of integrated circuit, as we can see here. Here we have a SMD chip. The first pin is coded with this rectangle pad, and the rest of the pads they have a different shape. So here we have an example. We have capacitor, as we can see in here. So we have the negative lead and you have the positive. The positive goes into this, negative goes into number 2, and here as you can see, you see the physical capacitor placed on the PCB, and you can see those two pads on the PCB. Same case in here, we have surface mount components. The surface mount component is basically you don't have a hole, it's just the pad on one layer on the top or the bottom, and the component will be placed on the same layer where the pads are and will be soldered from the same layer as well. As we can see here, we have soy chip and we have pads around underneath all these pins, and the chip is soldered to those pads as similar to this case. So these are the two common type of pads for soldering components. The other type of holes is called via. Basically, via is not used to solder component but to connect the traces between layers. So basically, they start by drilling the hole in here, and then they plate the inside of the hole to connect the top and the bottom layer of this via. And now you have a via, you have trace going on the first layer, then transfer to the second layer through this via, and the wall of this via inside is plated and it goes to the other layer. Now there are several types of vias depending on the density of the board. They can be blind via, buried via, and all different kind, which will be discussed in next. So either we have through-hole vias. Basically, the through-hole via, as we can see on this figure, connect the top and bottom layer and go through all different layers. So you have access to this via, through-hole via, from all the layer. So it can connect 1, 2, 3, 4, all of the layer together using one via. And the second type, it's called blind via. The blind via basically similar to this via and this via. They connect the surface layers into the inner layer. As we can see, this blind via connect the top layer into the first inner layer, and this via connect the bottom layer into the 1, 2, 3, the fourth inner layer, because this PCB has 6 layers. 1, 2, 3, 4, 5, 6. So this blind via connect layer 1 and 2, and this blind via connect layer 5 and 6. The third type of buried via called buried vias and connect two inner layers, as we can see, that are not part of the surface layers. So it's a start on one layer and end on the second layer, as we can see in here. So this one will connect 2 and 3, this will connect 4 and 5, and here also this will connect 3 and 4. Now the buried layer is not limited to two adjacent layers. It can start on one layer, it has to be inner layer, not close to the surface, and end up with another inner layer, not one of the surface layer. Now, the type of via that connect only two adjacent layers is called micro via. And this micro via only connect two adjacent layer. It doesn't pass more than 2 layers. So this one also in this case would be a micro via, and this one would be a micro via as well. Now the last type is called skip via. It's kind of micro via, but spans into more than two adjacent layers, basically adjacent plus 1, as we can see in here. So it's a span from 1, connect the 2, and then the 3. This one, same case, this one can be called skip via. Can span from the bottom one, 6, connect 5, and then go into layer 4. And the most commonly used is the through-hole via. And these are the most cost-effective solution to use. If you have a really high density PCB, then you will need to start using micro vias or buried vias, blind vias, and so on, but the cost will increase. Let's take a look at the second example before we make take a look at the comparison in terms of the price. So this is basically an Altium Designer. This is the layer stack manager. As we can see here, we have 6 layers PCB. The vias in here, so we have a through-hole via that connect all layers 1, 2 through 6. This is through-hole via. And then we have here buried via that connect layer 3 to 4, and we have the core in here between the layers, and then we have micro via in here that connect layer 2 to 3, and we have another micro via connect layer 4 to 5, and micro via that connect 5 to 6. As we said, buried via cannot connect the surface layer into an inner layer. It has to be inner to inner. Start with an inner layer and end up with another inner layer. Then we have the skip via. This connect layer 1, 2, and then you have 3, and this another skip layer that connect skip via that connect layer 4, skip through 5, and then connect layer 6. So basically what it says is skip because there is no connection between this via and via number 2, and this via here it's connect only 4 and 6, but it's a skip number 5. So as you can see, there is no connection in here. So cost wise, through hole is the cheapest solution, and this is the standard. Tinted is basically, since this via doesn't connect with any component on the top and bottom side of the PCB, they used to cover this via with the solder mask, which is the green layer we'll talk about later. So the second type of via, it's blind via. This will add slight cost to the PCB. And then if you use buried via, it will be even more expensive and it will need even more time for fabrication. If you add stacked via, basically the stacked via, there are multiple micro vias or multiple buried vias that connect layer to layer to layer, and this will be more expensive. And the last type, which if you have BGA with very fine pitch component, in this case you might ended up using via in bad. So we'll talk about this later in place, and this is the most expensive PCB you can make. Now the next element of it's called the solder mask or solder resist. It's basically a thin polymer layer deposit on the top of and bottom of the PCB to protect the copper from oxidation. That's the whole purpose of this layer. It's just to protect, give the PCB a nice look and protect the cover from oxidation. It's just cover these traces and isolate the air and stop any oxidation on these traces. And also it will help during the soldering process and prevent the solder from connecting to adjacent paths or to adjacent hole together. And the default color for this solder mask is green, but it's also available in different colors as well. It might be green, red, white, yellow, blue, any other color you can request. The cost might slightly increase if you change the color on green because the green is the standard, but usually it doesn't. So the other element is called the surface finish and also referred as solder coat or exposed conductor plating. It's basically they add a solder on the top of the pads and holes to make them easy to solder and also to protect them from oxidation, because the solder mask or solder resist goes over non-solderable joints. So here you can see these pads should be soldered. You have a solder mask, which is a layer you generate inside or from your ECAD design tools or from Altium. And the solder mask goes over the traces that do not have soldering joints. So if you have pads or you have through holes, you need to have a solder mask, and this solder mask layer is automatically generated by the tools. You don't have to worry about it. Now, these solder masks or these soldering points, they need to be covered by a layer to protect them or make the soldering easier. And this material could be tin solder, or it can be silver, mix of silver and tin, or could be gold as well, depends on the usage of the board. Now, what are the different surface finish we can have when we order a PCB? We have almost 5 or 6 different surface finish. The most commonly used surface finish, which gives the shiny look into the PCB, as we can see, is called HASL. Basically, HASL, it's hot air solder leveling. It's a type of finish used on the printed circuit board, as you can see in here. So after they are done, this would look like a cover. It's bare cover, and they cover it with this solder and give it this shiny look to protect these pads from oxidation, and also to make them solderable. So basically, the PCB is dipped into a bath of molten solder so that all exposed copper surfaces are covered by solder. This is how they do it, basically. And there are advantages and disadvantages for this technology. The most importantly, it's low cost. This is the super cheap technology to be used for surface finish, and it's basically the cheapest. Any other technologies might increase the PCB cost by at least 30%. And it's widely available, and also if you want to remove a component and solder it again, it's reworkable. So, and also it has excellent shelf life. Basically, after you do the finishing of the board, ship the boards, you can keep them on the shelf up to 1 year before you solder the component. Now, once you solder the component, you don't have to worry about them. There is no way they can oxidize because the solder will protect these pads. Now, the disadvantages of these is that you cannot count on these for high-speed signals, because the characteristic impedance of these pads is not good, as we will see later on. And also there are other disadvantages, but we can read through. So the second type is called immersion tin, which is a metallic finish deposited by a chemical displacement reaction that is applied directly over the basic metal of the circuit board or the cover of the circuit board. Now, it's called also ISN. Now, this immersion tin protects the underlying cover from oxidation over its intended shelf life. The shelf life for these it could be also between 6 months, almost around 6 months to 9 months. And this type of provide a flat surface. Unlike this, because these boards are dipped into a solder bath, you don't expect flatness on the top of these pads, as we can see. And if you have a fine pitch integrated circuit, it might be hard to align the pins of the chip into these pads. So in this case, if you have a fine pitch, they usually go with immersion tin. This is the whole difference between immersion tin and HASL processes. Now the third one is using silver. Basically, they dip this board into silver, and this provide excellent flatness on the surface of the board. And they usually go with this if you have a fine pitch BGA chips, and we will see this type of BGA components later on. But the disadvantages of this is it's expensive. It might be expensive. That's why they only use it in specific printed circuit board design. Now the third one, it's called OSB, or organic solderability preservative. Also they call it anti-tarnish, which preserve the copper surface from oxidation by applying a very thin protective layer of metal over the exposed copper. As we can see, this is the color of the copper. And if you look at all these PCB before they are finished, surface finished, they have this color, exactly this color, but they are finished with either a tin or silver, and here they add a protective layer on the top that only protect these solder joints, so it's organic. This layer, this material they are using are environment friendly and organic, and also this is cheap. However, the shelf life for these is like it's limited to 3 months maybe. And the advantage is also you have a very flat surface, and the solderability of these, it's not so good, it's not as good as these, and also the reworkability is not good as well, so it's not very commonly used between comparing to the other method. Now the last, or not the last one, we have something called ENIG, electroless nickel immersion gold, which is basically electro gold flash plating, which consists of a thin layer of gold over electroless or electrolytic nickel. And this type of plating is hard and durable. This is the whole thing about it. It also has a long shelf life. It can last for years. You don't have to worry about it. So if you need to make boards and put them on the shelf and do the assembly later on when needed, then you have to go with this because they have long shelf life. However, its durability and long shelf life make it more expensive than any of the finishes mentioned above. The gold protects the nickel during the storage and also provides the low contact resistance required for the thin gold deposit. Now, this technology is the most used finish in the PCB industry due to the growth and implementation of the ROHS generation, which is environment friendly, that doesn't contain a lead. Now, the last one called hard electrolytic gold, which consists of a layer of gold plated over a barrier coat of nickel. Now, hard gold is extremely durable and is most commonly applied to high wear areas on the PCB, such as edge connector fingers and keypads. They are not commonly used for pads and through holes. So unlike the previous technology ENIG, the thickness of the gold can vary by controlling the duration of the plating cycle. So basically this is not applicable to the solderable area, and it's only applied to the areas where we have direct contact, durable and rigid. So if you look at the comparison here, this is a final comparison. The question is which technology I should go with. Now, it's important to select the appropriate surface finish for your project by considering the various options while factoring in performance requirement and material cost. Now, for an example, if you are looking for the lowest cost, then tin lead or HASL might seem like a good choice for you, but it's not suitable for ROHS compliant products. If your product does require ROHS, you might consider lead-free HASL. That is only if there are no fine pitch components. Now, if you have a fine pitch component, as we saw, the HASL suffer from non-flat surface. So if you need to have a really flat surface for fine pitch component, in this case, you might need to consider the ENIG, and so on. So the most common two are the HASL lead-free and also gold NIG. So do we need at any point to use HASL that is leaded? Yes. For myself, when I design a board in the prototype stage and I might ended up replacing component on the board, solder and desolder, it's better to use leaded or use this HASL with lead, because it's easier to rework, it's easier to desolder. The temperature required to melt the lead tin is way less than the temperature required to melt the lead-free tin. Here you might need 130 degrees C. During the soldering process here, you might need to go all the way to 210 degrees C. That's why. So I usually start in prototype with HSL. Once I'm done and this is a final product and I don't really have a very fine pitch component, I go with HASL lead free to be environmental friendly. Now, if I have a fine pitch and I have BGA component, usually I go with ENIG. All three. I never used these. I never needed to use these as well. So the other element of the PCB anatomy is called legend or Silkscreen. If you look at any PCB board, you will see like white layers or markers that mark or define the outlines for the component, and it helps in the placement. Also, it provides legends for the components names or value as well. As we can see here, we have here an outline for this BGA chip, and also we have the number of the pins in here and the alphabet for the rows, and also we have the number of the ICs. This is IC101, this is IC151. This layer is called Silkscreen, and sometimes they call it overlay, and sometimes they call it a legend. And this is the last stage of the PCB manufacturing. So after they do the cover, clad cover laminate, then they compress all the PCBs together, then they drill, plate, they put the green mask, and then they put the finish on the top, and finally they print this Silkscreen layer, which is the last stage. And you will see all that in the video I will provide about PCB manufacturing. Now, how are PCBs made? There are several stages to make a PCB, and it's really very complicated process. And it's very the manufacturing plan for PCB is really high tech, and it's it's very expensive manufacturing plan. There is a video in here. It's for PCB Way, which is the company we are gonna use to make your project during this class. And it's super cheap, and they have very advanced facility. I encourage you to watch this video and let me know if you have any question about it. Now, what happen after we finish the PCB fabrication? The next stage, once the PCB is fabricated, you need to populate the component, or it's called the PCBA. Once you see this acronyms, it's called printed circuit board assembly. So basically, the printed circuit board assembly also goes into stages. First, they clean up the PCBs, then they apply the solder paste into these exposed pads where the component must be placed, and then they use robot machine, or called pick and place machine, to place the component in place. Then they use an oven called reflow oven to solder these components, because the solder paste is basically is the solder, it's the tin. Then they put the component, they put the board into the oven will melt down the component will sit on the top of these pads, and the solder will solder these joints into the pads, the component bends into the pads, and then if they have through hole component, they will run the board through a wave soldering machine. And after that, once the soldering is complete, they do visual inspection, or they can do something called e-test. It's also automated inspection. Then they go for testing and repair. Now, there is a video for PCB Way company in their assembly facility. You are highly encouraged to watch this video and let me know if you have any question. It's very interesting to see this video. Now, After we looked into the anatomy of the PCB and PCB manufacturing and assembly, the question might rise at this point. What are the PCB engineer responsibility in real? So PCB engineer basically it's not just constructing or designing schematic and layout and that's it. No, PCB engineer is required and responsible to define the classification of the product, define the mechanical factor because, or at least he has, or the he or she has to have like a collaboration with mechanical engineer to define the mechanical factor because eventually you are designing a PCB to fit inside a specific enclosure or specific product. Like if you are designing a fitness tracker, for instance, there is a specific shape for the PCB and you need to design according to the mechanical specifications. Also environmental uh, operational environment. So what kind of environment this board will operate from minus 40 degrees C up to 70 or 80 degrees C? In this case, you need to have awareness of the components you need to select and use in your PCB design. For instance, if this component has to work outdoor, when the temperature goes down to minus 10 degrees C, you need to make sure all the components you selected can have operational range goes to that operational environment. Design guidelines, quality guidelines, all these different factors you need to be deeply involved. PCB material, as we mentioned earlier, what kind of material you need to use, what kind of finish, all these are determined by the PCB engineer. Manufacturing technology, and as we will see later on, before you start designing your PCB, you need to make sure that this PCB can be manufactured. So, for example, if you design a PCB with traces that are 1 mil, that have a width of 1 mil, these are not manufacturable. They cannot be manufactured. They are not manufacturable. So you cannot design something like that. You need to understand um, what are the limitations, what is the capability of your manufacturing company, PCB manufacturing company, same case for assembly company as well. Also, you need to define the test technology you will be used because you are designing the PCB. You need to put test points on the PCB. You need to define how this board will be tested. What are the requirements for testing this board? Cost and time. When a project is assigned to you by the other team and you are responsible to design the PCB, well, they will give you limitation. They will tell you we need to design this by $50. Now you need to do a feasibility study to understand how we can design this board by the cost limited by the business case. So it's not beneficial for a business case to design a PCB for $250 while the business case will say you need to do it for $50. So you need to understand all the factors, limitation, restriction, and how you can do it, or if it cannot be done, you need to say it cannot be done, and what is the time frame on that. Also, the other options like how you can protect the environment when you deposit the PCB and what are the functions of this PCB. Now, when we talked about the capability, we need to understand the capability before we design a PCB. For instance, here we have PCB way, which is PCB manufacturer's cheap, and you will see the capabilities on any PCB manufacturer website. So if you look here, they will tell you the maximum number of layers they can fabricate is 10 layers, 1 to 10 layers. If you design a PCB with 12 layers, you need to go into a different manufacturer. If you have to stick with this manufacturer, you need to understand that the maximum they can do is 10 layers. And also for the material, they only have FR4 for the insulation material and or aluminum. And in this case, this is what they can do. They can do flex, rigid flex, metal base, and so on. And the maximum PCB size you can design is this. So you cannot go bigger than that or smaller than that. Same case, if you need a thickness, this is what they can do. If you need, let's say, minimum trace, So what is the minimum trace width? It's 4 mil. You cannot design a board with less than 4 mil. They cannot fabricate. Also the thickness and so on, the smaller drill and so on. You need to take a look at all these limitations before starting your design. If you have any question, you should contact them before you start the design as well. Same case goes into so PCB assembly. As you can see here, there are capability for each PCB assembly house to do assembly. It depends on the basically the limitation is the pitch of the components, how fine they can place a pitch component, how much fine you can go down. You need to read through, can they place through hole and SMD component, can they place the SMD component on both sides or a single side, and so on. So you just need to understand the capability of this assembly plan. If they don't have enough capability, you may search for a different assembly house. Let's say if we say search advanced PCB let's say capabilities. Let's take a look, for instance, advanced PCB capabilities, advanced circuit. So they will mention it here, layer drill size, full list. Let's take a look at this. I use this company also. Let's say they can go up to 40 layers here if you are using FR4. So comparing to 10 layers, now you have more advanced PCB fabrication factory. And you can see all these different options to use during the design. So the question now, after all these basics and this introduction, how new products are made really in industry? And you really need to understand this concept in high abstract level before you start learning or making products, because there are processes defined how you design product, even a very simple product in real industry. So basically they look first, they build business plan, and this business plan they do market analysis and all different kind financial analysis, and they will study the company share in this domain they are gonna move forward with. And after that they start the second to put a company perspective. And basically as a design engineer you come into stage 3, which is the product development stage, or gate 3, after the business plan is developed by the company. In the product development stage there is a roadmap and there is a concept design and prototype, which goes into VMV stage in here. So you design prototype, you test, go iteration 1, iteration 2, and iteration 3. And this stage is done based on systematic process, and which will we discuss in the next slide. So basically you design a PCB, source select the electronic components, generate bill of material, send your product to the fabrication plan and PCB assembly. This is the life cycle of PCB or product design when it contains PCB. Now, but how this is done as a PCB design manufacturing process. So you start with the circuit diagram in the schematic, or they call it design capture. You generate the layout, and then you order the boards, then do the assembly. This is what we mentioned earlier. But what is the process? There is a systematic process, and this systematic process differs from company to company. And this is what I usually use. So basically you have a product concept. And the product concept either is generated by a business plan, or it's just an idea by the R&D engineers. And this product concept will have a requirement that are defined based on the market or voice of customers. And this requirement could be high level requirement, electrical requirement, functional requirement, mechanical requirement, and environmental requirement as well. And you need to have a deep understanding of these requirements, and they will be provided to you as a generic. You need to have more in-depth analysis on these requirements. At the same time, you have restrictions. Always companies try to design a product in the lowest cost. Cost comes on the first all the time. They need to design superior product at the lowest possible cost. Then the size, it's the age of mobility. You have everything is mobile. You have to design small things that are lightweight. They can run on a battery for a long time. These are the most common restriction: cost, size, weight, energy, budget. Everything now is mobile, running on a battery. Now, you look into these requirement and restriction and do a feasibility analysis as an engineer, design engineer. Now, based on this feasibility analysis, you put this requirement, you understand the requirement because they are the design objective for this product. For instance, the cost, we need inexpensive. The setup, we need to design something. For instance, it's not intrusive. You don't need to do any work for it, intrusive work for it. Energy budget, let's say it has to run on a battery. If it's, let's say, for a month or something, lifetime portability, etc. You need to define these requirements in details. Then, based on the feasibility study, you say, okay, we can design this product, but the restriction has to be so. So you put the result of this feasibility study and say, we can design it for the specified cost at this, providing these features. Now, the kick-off stage comes next, where you need to finalize the specification of the design, put the design architecture, do project planning, and allocate all the resources needed to complete this project. Now, functional or design architecture, when we look at design architecture, we are talking about, it's not circuit design, it's high level. What are the elements of this board you are going to design? For instance, if we are designing a sensor, which will be a project for this course, we are going to design a traffic sensor that is wireless, running on a battery, that is dedicated to count vehicles with no contact with the vehicle. Basically, you need to place it on the top of the surface, of the road surface, and whenever a vehicle passes over the sensor will be able to detect this vehicle, measure its speed, and do classification, transfer this data in real time with a timestamp to an access point, and also provide local information by using a GPS module, and measure the vertical acceleration of the road surface, store the data on a local data logger, and also transfer the data when needed. At the same time, the sensor can harvest energy from the solar sun. So these are the components. As we can see, we need intelligent microcontroller, we need energy harvesting unit, we need sensors, couple sensors for detecting vehicle. In this case, we are going to use magnetometer sensor and an accelerometer sensor. Magnetometer sensor will measure the disturbance to the Earth's magnetic field caused by overpassing vehicle. We are going to use accelerometer sensor to measure the vertical acceleration of the road surface caused by the vehicle axles or wheels. We have serial flash memory and micro SD memory to store data on the sensor. We have power management unit to distribute the power. We have battery gauge to measure the battery capacity. When you have energy harvesting unit to harvest energy from the solar sun. Also, we have wireless module to transfer data to the access point. We have GPS module to get the localization information of the sensor, etc. So basically, you define the high-level architecture of the system based on the requirement, and these requirements are known from the previous stage. Now, next, you go into more details about the system architecture, how the various components inside the system interact together. So here you see everything in orange is basically the power, everything in green and blue, everything in green is data, everything in blue is control. So this is the system architecture. You have a core component, which is a microcontroller. Here on the input, you get the energy harvested from either the sun or thermoelectric, piezoelectric, or RF. Also, you have wireless charger. Then you have storage. We have not yet selected what kind of storage power or energy storage we are going to use. Then we have a power management and energy harvesting unit. And then we have a fuel gauge that measure the battery capacity. We have load switch to turn on and off the peripherals we have on board based on the available energy. We have wireless transceiver to communicate wirelessly. We have GPS for localization. We have data logger over micro SD card, and we have all the sensors. So this is high level architecture. You design your system. I know it's a little bit complicated, but don't worry about it. It will be simplified by session after session. So then you look at the general architecture of the system. As we said, we need to design a traffic sensor that can detect vehicle, measure the speed of vehicle, do classification, calculate travel time, etc. So basically, this is the sensor I designed. So you are gonna work on a project that really exists as a product and being used as well. So this is the sensor. It's called IVCCS, Intelligent Vehicle Counting and Classification Sensor. We put this sensor into enclosure, and this enclosure has a solar cell, as you can see in here, to harvest energy from the sun. Also has battery inside. You place the sensor on the road surface. You have two sensors on each lane with a predefined distance to calculate the speed. As this sensor will communicate with an access point on the road shoulder, the access point will communicate with web server or remote web server over the cellular network. Now, we only will focus on this sensor. We are not going to focus on the access point and the other stuff. We need to design this sensor and try to implement that. It's easy. Now, here how you look at the scalable system architecture. Now, here we are looking at sensor placed at one position. Here, how the system can be scaled. So you have multiple sensors connect with one gateway. So each 16 sensor connect with one gateway, and this gateway connect with the server over the cellular towers. And the cellular towers provide the data to the internet cloud, where you have the server and you can control all the data. You can see all the data in real time at city level or state level. And these access points are and sensors are distributed all over the roads. So this is the high scalable level of the system. You need to think at this level. The next stage, you put the architecture. Everything have been done in the previous stage is just conceptual level. It's high abstract level. Next, now based on that, you have all the factors, all the functions, and all the restriction, including the cost. You need to start component selection. Component selection, they are governed by the cost, the weight, the energy or power consumption of these components, and other factors. So you know what kind of battery you are going to use, and in this case, you know the capacity of the battery, so you need to select the right component and calculate the energy budget after all. So to do component selection, basically, you need to put the criteria for every single component based on these restrictions and requirements as well. Because it's true that you need to conserve energy, but at the same time, high performance is required. You need to be able to do a sampling rate, let's say at 100 megabit. In this case, you need high-speed analog digital converter, and you need high-speed microprocessor to be able to process the data and do all different kind of intelligent algorithms. So there is a trade-off always between cost, energy, and performance. You need to find the balance point where you can find the right solution for your application. And when you do component selection, it's not like you select a component and use it right away in your design. No, you need to do something called rapid prototyping, where you can use whatever available toolkits to evaluate the component you have selected for your design. And this is what comes in here. Before you move to the next stage, which is the design, in component selection, you have rapid evaluation and simulation using whatever available kits and IDEs, integrated development environment, and you count on the datasheet, reference design, application notes during this stage, and you have criteria for these components. We can take a look in more details in the next slide. For instance, when we talk about microcontroller, for instance, as you can see in here, as I mentioned, this class is not about just designing PCB. No, you need to learn the processes of designing a real product. You need to see what kind of criteria I need to design before I start just opening the ECAD tool or Altium Designer and start grabbing component and put them on a board. No, it's not like that. The easiest part is to grab these components and put them on a board, do the layout and send it to the manufacturing plant. But does it provide the right functionality? Does it meet all the market requirement? No. You need to understand all these aspects as a design engineer. You need to be part of these processes. That's why I'm trying to focus on these during this session, and in the next session we will have a time to focus on the design. So it's just one session we have this, but after that we'll move forward with the design. But let's try to understand these factors first. So for instance, we have a microcontroller. As we saw, we have 32-bit microcontroller defined in the block diagram in here. It's the core component, it's the heart of the system in here. So how we can define criteria for this microcontroller? As we know, this is portable sensor. It has to run on battery for 10 years. So we need really ultra low power, high performance microcontroller. So how we can combine these two, ultra low power and high performance microcontroller? In this case, we need to understand the characteristics of the ultra low power microcontroller. And these characteristics are well known in industry, as they have multi-operational power modes. They have very low power consumption in active mode, and so on. So each one of these, we are not gonna go over them and explain them because it's not the objective of this class, but you need to understand these. And if you search or you Google, you will find these results right away. Now, once you understand these and you try to open a datasheet for microcontroller, you will see values for these, and you can start comparing these parameters with other components. So you select a microcontroller. What you need to do is to order a kit for this microcontroller like Niclo or Discover or any other evaluation kit, and to try to take some real measurements. Now, the values defined in data sheet, you need to be very careful about these values. For instance, they will tell you the power consumption in active mode. If you have the analog digital converter running and the CPU is running at 40 megahertz, the power consumption would be, let's say, 100 microamp per megahertz. Now, you need to be very careful about this because this value is defined in an optimal condition, meaning these values are defined at 20 degrees C, which is the temperature room, and you don't have any leakage current by the surrounding component connected to the microcontroller. Because when you need to power up a microcontroller, you need coupling capacitors on all the power pins, and there is a leakage current by these coupling capacitors you need to take into the account. So that's why you need to start take real measurements. If your system is really sensitive to the power consumption and its energy budget is very critical, you need to take real measurements. Same case for the performance and so on. So basically you can grab any kit for the microcontroller you selected, or you can use any microcontroller from the same series and do some experiments. And this is called rapid prototyping because you don't have to build a board. You can grab this microcontroller. Now, if you select sensor, as you can see here, the energy harvester, also you need to do a characterization for the power consumption. You can bring the kit for this chip, and almost every these major chips they have kits you can use. You can connect now this microcontroller with this chip, try to control it and build the firmware for it, or collaborate with a firmware engineer to do some testing. Now, everything you build at this moment as a driver can be reused later on. So it's not waste of time. Once you are done with the characterization and definition, defining the criteria and select all your component based on the performance, the cost, the size factor, and all different criteria you had, you start the schematic design. When you design schematic for every single component, you need to go back to the datasheet, reference design, application note. Because if you use a chip, there are a specific requirement in the datasheet of the chip, how to put the chip on board, what kind of coupling capacitor you need to connect with it, what is the width of the traces you need to connect with it, and so on. There are very detailed requirements, and we will see these requirements when we start designing the boards. We need to go for every single chip we are using on the board or active component. We need to look at the datasheet, reference design, and application note. We need to design with full awareness of the chip requirements. Then you have design rules and consideration on the other side. If you are designing high-speed printed circuit board, you need to consider mixed signal, power signals, differential pairs, impedance control, crosstalk, and all these factors. Also, we will study them in details. And as long as you are not designing something above 20 megahertz, you don't have to worry about signal integrity. It's just rule of thumb. Once you are done with the schematic design, as we will see in Altium, we will run something called electrical rule check to make sure that there are no electrical problems in our schematic design before we move to the next stage, which is the layout. Now, stage 5 comes later, which is the layout design. Basically, you transfer this electrical diagram you created in schematic into a physical board where you have the physical components. In schematic, you have the symbol or the schematic representation of the component. In layout, you have the physical component or the actual size and footprint of these components. You need to lay them out on the board and start routing them together. And before you start routing, you need to go back to the mechanical specification. Why? Because you need to know what is the size of the board, what is the shape of the board, what is the thickness of the board, and all different mechanical specifications. Because these mechanical specifications are provided by your mechanical engineer who designed the enclosure or the final form of the product. Then you need to start working on layer stack specs. How many layers you will need for your design, how many planes you will need, what is the thickness of the PCBs, how many vias, what kind of vias you will need, and so on. How you can estimate the number of layers needed, we will talk about that in place as well. There are some rules that will help you to estimate the number of layers. Now then, before you start doing anything, you need to set the design rules. What is the minimum thickness of the wire? What is the maximum thickness? What is the minimum hole size? What is the hole size of the vias? What is the size of the vias? We need to define all these design rules. And all these we are mentioning right now, we will see them in practice. We'll learn how to do them, how to define them, how to use them, how we can calculate the via size based on the current, based on the impedance, and so on. Then, if you don't have the components in libraries, you need to design these components, design the footprints for the components. Then it comes placing the components on board. Always when you place the component, as we will see later, you start with the connector that provide an interfacing to the outer world. Then you can place the core component and other surrounding component. Then you start routing the buses first, data buses and traces. Next, you create copper pools to improve your signal integrity and provide lower impedance to the ground. And then you do design rule check. In schematic, we did electrical rule check. In layout, they call it design rule check. You need to make sure whatever you did in here comply with the rule you specified in here. Then you run signal integrity analysis and power integrity analysis. Make sure that the impedance is right, the distribution of the power traces is correct. Next, once you are done with the layout and all different kind of the checks, you finalize your layout, you do fabrication file generation, which are the fabrication file needed for the fabrication house or fabrication plane. Because when you send your PCB to PCBA, for instance, to fabricate your PCB, you don't send the design. The design is you should keep it. No one should see it. This is property for your company. You only send something called manufacturing files or Gerber files, and we will see how we can generate these files, how we can do an edit and review for these files as well. But for now, take this process as just high abstract level, because we are gonna move over each one of these stages one by one. In addition to fabrication files, will include the bill of material, what are the components you used, and what is the manufacturing part number for this component, what is the supplier part number for this component, how many you used of each. Then you have the fabrication file for the PCB, or It's called also Gerber files and mounting and drill files. Then you have the mounting files for the pick and place machine during the assembly process. It's called XY files. It's basically provide the coordinate for every single component in X and Y coordinates. Then if you have any reference notes to provide for the manufacturing, you put them. Layer stack specification for the PCB fabrication, and if you have a 3D model for the board, it will help during the assembly. And then you send these files into the PCB fabrication and assembly, where you should get the board that works from the first time. Here is the board we are gonna work, and this is the 3D model of the board we are gonna use as our project. So basically I will provide you the schematic for this design, and you need to redo the schematic in Altium. I will provide it as a PDF. You need to redo it in Altium, and you need to do the layout as well in Altium. So you can have this as a reference for you. And this is basically what we talked about, is the sensor. And we will explain it in place later on. So once your PCB is fabricated, and in reality, you collaborate with software engineer to start developing firmware and testing different peripherals on board. And you go into V&V cycle. So you have hardware prototyping, firmware development, you use a modular approach, you design a specific functionality or module or driver for a specific chip on the board, you do integration with the hardware, do debugging, then design the next. It's module by module. You need to make sure you don't want to design code to run all the functions on the board one time, because it's going to be very, very hard to test. Now you design a single module, test it, do debugging. If it works, design the second model, and then you do something called system integration, where you integrate all the function on the system and start doing verification and validation. The validation or testing in this circuit is at the code level. Now the validation and verification here is at the function and product level. So here you will do functional testing. You need to make sure that all the intended functions are doing what's intended. And these functions are defined by the market requirements. Then you do performance testing. You make sure that you measure the current, make sure that the power consumption as defined. You do environmental testing. Environmental testing, basically, when you design a product to work from minus 20 degrees C all the way to 70 degrees C, you need to do testing and make sure the product will stand for this temperature. Basically, we use something called environmental chamber. The environmental chamber, it's like accelerated kind of testing. We put the sensor or the product inside this chamber and take the temperature all the way down to minus 20 plus some margins, and look at the function of the system by tester that is positioned outside the environmental chamber, and start collecting data to make sure that the system is working as intended. Now, then we do increase the temperature all the way to the maximum temperature and do the same test. Also, you do shock test, interference test, and part of it you do electromagnetic interference test. Make sure there are no radiation from the system. If you need to go for compliance by FCC or IEC or UL, whatever, you do power evaluation. As we said, we need to make sure that the consumption is according to the specification we had, and make sure that your signals transferring between components are they have right rise and falling time. You can use oscilloscope for that. And then if everything looks good, you can go for the certification if you need a certification for your product. Now, if you want to distribute your product in a market like Europe or United States, Canada, you need to have some sort of certification for your product to be able to distribute that product. So you need to make sure when you design your product, you design according to this certification. And once you are done with the certification, the product is ready for release. And this is the last stage of the product. Now, what if during the design process or after the design process, you decided to change your mind because you selected the wrong component? Let's say at this stage during the validation and verification, you realize that you have radiation on your design and you cannot be certified by FCC because you are above the limits for the radiation, electromagnetic compliance. So at this point, it's basically you are at the startup. You are very close to startup. You are done almost at startup in here. So in this case, the cost for that will cost you to redo everything. It's 100%. Now, if you are doing the development in hardware here, prototyping, during the prototyping in here, and you are testing, it's fine. The cost could be around 30%. If you are doing the design at the first stage, when you are selecting component, doing iteration 1, iteration 2 to test the hardware, it's 3%. Now, it becomes worse when your product is released and you have to do something called a recall, and this the cost can be 300% of the production. Sometimes you hear by Honda they have a recall for specific vehicles because the airbags have some problems, and the cost for this recall is tremendous. It might cause some companies to close. So you need to be very careful. If you have anything to modify, you need to modify it through the design stage. If not, during the development. Once you pass the development, you need to make sure that your product is 100% according to the specs that defined at the beginning. So before the last part of this presentation is why we want to select Altium. What is Altium Designer? Altium Designer is basically a printed circuit board design software that is made for designers to create world-class PCB design. And it's the only PCB design tool with unified design data model, meaning it combines mechanical design model, electrical design model into one unified environment in addition to the supply chain. Now, this is something very, very unique and very handful. Within one tool, you can do simulation, you can integrate your mechanical design and see how the electrical design or the printed circuit board will fit into the mechanical design. Or you can export your printed circuit board for mechanical engineer and do collaborative work within the same environment, so you can adjust your mechanical design and everything. Also, you can select your component and link them directly or automatically into the supply chain with updated price for every single component, and see how much available component in stock at the supplier in real time and find alternative parts inside one single environment. Now, they are growing very fast. It's really, really fast, and they have several updates every single years. And Altium now is on the top of the list of most utilized ECAD tools. Take a look at these surveys. You will be amazed by the progress they are making. And if you look at market share by revenue, in 2014, they have around 12-13% comparing to Mentor that used to take over the market by 35%. Now in 2019, they overpassed actually Mentor by the number of users, but not by the revenue, because Mentor tools are really expensive. They are highly expensive and very high-end tools. It's not meant for any user. Intel, for instance, use Mentor. However, the whole industry start transferring into Altium Designer. So as an engineers or as a company, we need to make sure about the decision we need to make for tool selection. You need to select a tool that will be supported, and if any graduate student or engineers transferring from company to company, they have experience with these tools. If you select a niche tools, even if it's free and no one is using these tools, it's not going to be beneficial for your company, because you need to spend a lot of money and for training the new engineers on using these tools. And if you look outside, you might not have enough resources and enough support for this tool. So that's why it's very critical to select the right tools for the engineers inside the company. Now, Altium they have projection, they will dominate the competition before 2025. Look here. They are looking by 2020 to have revenue more than any company. Again, in terms of users and must utilize tools, Altium is on the top. I think 50% or even more than 50% of the industry uses Altium. And let's skip this. We'll come back to, if you look at the high profile customers, it's amazing what companies are using Altium right now in terms of aerospace defense, like NASA, SpaceX, in terms of automotive, Audi, Mercedes, Volkswagen, Toyota, Honda, Tesla. Everyone is using Altium. Amazon is using Altium for designing ecobee and all the different IoT stuff. If you look at the major semiconductor companies, it's Altium is adopted by every single company. Now, if you want to transfer and work for any of these companies, you don't have to learn new tools. They are already using these tools. You can just put it on your CV and it will be beneficial for you. So again, Altium provide like a direct transfer from concept to realization within one unified infrastructure, one unified design tools, where you start from putting your idea into a design, into combining this design with a mechanical design, doing the simulation, and all the way to realization, and especially when you use Altium 365. Now, these are some statistic information about the PCB design market, just to realize how important the role of PCB design engineer. So the revenue or the share for just electronic design tools, it's $2 to $5 billion, the estimation for that. And if you look printed circuit board, we are talking about $100 billion. And they needed design engineers to generate all this revenue. And they are looking, there is like now in industry for hardware design engineer and PCB design engineer. It's a tough job, but it's highly paid job, and it's really I like it. I love it. I love to be a hardware design engineer. It's very interesting because you are designing tomorrow's technology. You have major role in the decision making in your company when you design this product. Everyone is counting on your knowledge, experience, and the right decision when you design this product. Now, again, if you look at high-tech product companies, basically they have the product realization is a composition of three segments. Basically, three segments of the value chain, of course. So the first value chain is basically the design tools used to design the product. The second value chain is basically the part value chain or the supply chain of the parts, how you source these components. The second value chain is the manufacturing of this part. Now, Altium is trying to combine all these three together. And for now, if you look at Altium Designer 19.1, the design tool value chain and part value chain are combined in one tool. Now you don't have to switch between the tools to work out these two segments. They are already combined, and Altium 365 also is coming soon to combine the manufacturing value chain as well into the same unified environment. Now, how to install and activate Altium? You need to have an account and you need to have these following steps. You need to go online and have these following steps. If you don't want to buy a license and you want to try Altium, you can request a demo license for 15 days or 14 days, and you can request like an expansion for that up to a month, I believe. So for students at University of Oklahoma, I put a tutorial on Canvas for how you can use a university license for that. Please take a look at that license. Okay. Thank you all for your time, and I know it's long presentation and this is just introduction. Next presentation we will try to get into more information about using Altium Designer tools, and we will try and start to implement all these steps we talked about during this presentation and start design real PCB based on a solid background and knowledge how to design product. And we will start with learning or reviewing some electronic components their symbols and photo-prints as well before we dive into Altium Designers. Over the next session, we'll have first part of the session discuss some theoretical or best practices aspects of hardware design or printed circuit board design, and then we will have the hands-on part in the next at the end of the session as well. Okay, thank you all for your time and looking forward to talk to you on the next session.